session, we are going to see the Verilog code, how to write the Verilog code for the synchronous counter. So, what is synchronous counter? The counter is comprised of flip-flops. 4-bit synchronous counter means you will have 4 flip-flops in the circuit. So, it is one of the sequential circuit. And the synchronous indicates all the 4 flip-flops will be driven by the same clock. That means all the flip-flops changes its state at the same time. So that is the synchronous counter. So let us see the circuit. So it is a 4-bit synchronous counter. All the 4 flip-flops are driven by the same clock and the output is taken. So it is in the counter means the initially all the flip-flops are at 0 state and it is being constructed using the T flip-flop. In the D flip-flop, when the input is 0, the output will be retained as the previous state, and when the input is 1, the output will be toggled to that. Okay. So when this circuit is constructed like this, this counter is implemented at every time the value is implemented. After 15, again it is going back to the same value. So this is the circuit. So now we are going to write the Verilog code. That is why we are going to describe this hardware using our Verilog code. Like the previous videos we have discussed about the ripple carry adder. So it is constructed only using a combinational circuit. Therefore, we used a structural modeling or gate level modeling for writing the code. Whereas for the sequential circuit, we are going to describe this behavior of the circuit. Therefore, we will be preferring to use the behavioral model to write the program. So let me explain that. Okay. So this is the code for our 4-bit synchronous counter. So it comprises of 4 flip-flops. As in the concept of instantiation, this flip-flop T flip-flop we are going to use 4 times. Therefore, first I am writing a basic module. This instance I am going to write. So this is the code for the T flip-flop. In the T flip-flop, what are the inputs? Clock is one input and the T is another input and output is going to be the Q. So Q comma clock comma T. Therefore, I am declaring those 2 variables. This clock and Q are the inputs and output is Q. And then this register is also a temporary variable. It can store the value Q. Initially, what is the value of the Q? It is going to be 0. Okay, and this is a very, very important instruction in the Verilog coding. Always at negative edge of the clock. So when you want to do that, when you want to make the flip-flop to change its state. So always at the negative edge clock. So clock with a negative edge, this is going to change its code. Okay. So when that negative edge comes, it wants to carry out some set of instructions. So to group those instructions, we have the keywords begin and end. Within this group, we can use the set of instructions. Within that group, we can use the set of instructions. All these instructions will be executed under that condition. When the clock is coming to a negative edge, these all instructions will be executed. In this case, we have only one instruction, that means it has to toggle its value. So what is the symbol for it? It is the XOR symbol. But the XOR means it is 2 inputs. But here we have one bit, that is referred as 1 bit XOR. We refer it as 1 bit. That means it simply toggles the value. When it toggles the value, when the input is 0, it will not toggle. When the input is 1, that value will be toggled. So this is the case we have. And then we have an AND module. So this is our basic instance. Now, in the main module, that is the synchronous counter. The module name is synchronous counter, and it is a 4-bit synchronous counter. Therefore, this T flip-flop module has to be instantiated 4 times. It has to be called 4 times. Now, we will see the main program. In the main program, again we have the keyword module. What is the name I have given? Synchronous counter. In short form, I have given. It is our user friendly. If you can fix any name. And here also this clock and data are the instead of T as we know the thumb rule. Whatever the variables we used in the basic instruction, that should not be repeated in the main program. Therefore, I am giving this in the different way and this. Okay, so input clock and then input data. You see that Output is going to be my 4-bit value. So therefore 0, 0 to 3. That is 4 flip-flops are taken and its value all together is taken to derive a value. And then the first, what is the name of this module I have given? TFF. Therefore TFF. And what is the name I have given for each module? This is A, B, C and D. Therefore, this is the name of the module, so the name of the instance. The first instance is referred as A, second instance is B, C and D. And then, what is the input for the first flip-flop? You see that clock is there for every flip-flop and another one is the data. Data is given directly. Therefore, here the clock is given and the data is given. Therefore, clock and data are the inputs and the output is going to be Q of 0. Now you observe the circuit. For the second flip-flop, what is the input? The output of the previous flip-flop and the data are added together to produce an input for the second stage. Therefore, previous output is Q of 0 and the data are added together and the clock is the same because it is synchronous counter and these two are given to produce an output Q of 1. Okay, similarly Q of 2. So how does the Q of 2, that is for the second flip-flop, what are the inputs? The input is the previous stage, this ANDed output along with the state of this one. Therefore, already you have ANDed this data Q of 0 and this Q of 1. And similarly the last one. And then the final keyword is an AND module. So this is the descriptive way of writing the Verilog code for our synchronous counter. Now what will be the output? How will you check the logic of the circuit? By checking its RTL and our test bench waveform. That we will see now. So this synchronous counter, it is going to this RTL will be describing the abstraction level of the circuit. Therefore, clock and data are the inputs and the output is a 4-bit byte output. Okay. Now let's see this test bench waveform. Right. In the test bench waveform, the clock and data are the inputs and the output is a 4-bit. And then assume that I will get the marker at this stage. So this value only is getting if 000, that is the value displayed there. But initially you observe that this is my clock. Okay, and then in the main program, what we have written? Always at negative edge clock. So where we have a negative edge, this is when the high and low transition. So this is a negative edge. So during this negative edge only, this count value will change the states. Before 0001, the next value will be 0010, 0011 and so on. All these are this negative edge, it is changing its value. And then this marker value is getting displayed here. Okay, so this is a rectangle. Once it is 0, 4 bars, then again it comes back to 0. So this is the test bench waveform. This gives the visual representation of our possible inputs and the